halfway across the world because I'm obsessed with arrays and I want to talk about it. Array programming is really productive. Oftentimes we see array programming with things like collections of collective operators like plus or times and NumPy. Sometimes we see array programming with these einsum interfaces, kind of generalizing this concept so that you can have any pointwise expression on the right-hand side and it sums over the indices. These frameworks have really shaped how we think about productive programming with collections of data. And array programming is a really core concept for computer science. It's one of the first data structures that we teach. It's in many programming languages. The semantics of arrays are roughly the same everywhere. And these frameworks are really well implemented. They're pretty fast. We're reaching peak machine throughput for a lot of these systems. But one thing about these frameworks where they fall short is that they really only represent dense arrays. Data in the real world has structure beyond this dense rectilinear grids of data. In scientific computing, we often see these triangular matrices. So this arises when you're doing a solver and maybe you only store the upper triangle. We might see a banded matrix, something like a symmetric matrix. Scientific computing also gives rise to sparse matrices. So in this example, perhaps this sparse matrix is representing this triangular mesh. So the rows are triangles and the columns are triangles they might be connected to, and we say that a non-zero represents one of these connections. In domains like machine learning or quantum computing or finite element methods, we may see different kinds of patterns of sparsity where the non-zeros occur together. And this is an opportunity for further optimization. Additionally, of course, in machine learning, we might do a convolution. I'm a compiler writer, so I don't like to support this I minus j kind of thing, especially on my sparse arrays. But one interesting thing is we can recast operations as structure sometimes. So in this case, if we wanted to represent convolution, we might recast this I minus j as a matrix of circular shifts of the filter. And now convolution has become matrix multiply, and I'm happy again. Of course, if we're doing convolution, we might want to pad the matrix, and padding is yet another kind of structure. And moving on from just sparsity, we might see structures that represent something like repeated data. So in this case, instead of storing redundant adjacent pixel values, we'll store the color of the pixel once together with the number of times it occurs. This is a really useful optimization in something like a computer-generated image, like a screenshot. We also see run-length encoding occur in databases. If you're doing a column store and your entries are sorted, you might see adjacent values that are the same. So here we can annotate some of those runs and use run-length encoding to store the columns. So there's a lot of different structures that we might see, and supporting this structure is really challenging. It was easy in the dense case because dense systems have this property where they're kind of self-similar from the theory all the way down to the hardware and the systolic arrays. It's all rectangles all the way down. Critically, the relationship between where entries are represented in theory and where they're stored in memory has a really clear correspondence with like this row major one-to-one relationship. Whereas when you have something like a sparse tensor, this relationship is broken. So if I was talking about this adjacency matrix where we have triangles connected to triangles, triangles only have 3 sides. So there's a maximum of 3 non-zeros in each row. This means that we should probably only store just the non-zeros. Storing the entire matrix would be an asymptotic overhead, and on some systems it wouldn't be feasible. So another optimization that we might want to do is that we actually may want to modify the computation itself to match this storage optimization. So we may want to avoid multiplication by 0, for example, because x times 0 is equal to 0. So we really only want to process these elements. If we stored them using a standard format like compressed sparse column, we might store an array here. Val is the non-zeros. IDX might be the locations of the non-zeros within each column, and PTR is going to be the delineation between columns. So we see that the relationship now between where they're stored in theory and where they're stored in memory becomes quite complex. Existing compilers tend to restrict the control flow that they support so that they can handle these more complex structures. So oftentimes they'll still use these high-level collectives to express a more constrained version of an input program, and then they'll use scheduling languages to express a restricted set of optimizations that they do support. Something like compute at to use a temporary, they might reorder or split loops, or add some pre-computation, and you can have different schedules for different situations. So we can kind of characterize this trade-off between program flexibility and array flexibility with this feature matrix. Halide is a very popular dense compiler. It supports only dense arrays, but it supports a really wide variety of control flow constructs on those arrays. Taco supports combinations of dense and sparse arrays, but at the cost of some kind of control flow features. We see a sort of proliferation of different compilers for different kinds of structure. So this Cora compiler, for example, is a compiler for ragged arrays. There's a trick that you can do to support more kinds of control flow. If you restrict your attention to only one structured input, you can kind of use that, the structure of that input to guide the execution of the program through the control flow. So that's a trick that Tai Chi uses to support a much wider set of programming constructs. But of course, in this talk, we will show you how you can have both. So to give an overview of the kind of system that we're building, we're going to allow you to express high-level control flow directly with loops. And then we'll have a parameterized format description language that allows you to express a wide variety of formats for different use cases. They'll be combined with our compiler, and they'll produce efficient executable code that only stores and processes the non-zeros. Starting with the control flow, let's take a simple example where maybe we'd like to do a dot product on only the even values of two arrays. So you might write that in the Finch language like this, where we declare the output as 0, and then we sum up these pairwise products if they're even. And that would lead to a little bit of output pseudocode that iterates over the intersection of A and B, and then if the index is 0, then it adds it to this sum. Of course, if there may be different situations depending on the sparsity of the inputs that you may want to take different approaches. If A is a very small list of non-zeros, then maybe we want to filter that first. So the idea here would be that we only find the even values of A, and then we can go ahead and do that dot product. So this is how we would write that at a high level in Finch. And then the Finch compiler goes ahead and automatically generates some code that looks like this. So here we can see we iterate over the non-zeros of A, and then we do the intersection. And then, of course, maybe we want to do the intersection first, the filtering after. That might look like this. And you can see that each of these strategies may be better or worse in different situations. So being able to express different control flow is really important for the performance of the program. I'll move on from talking about the control flow language to the language of structures. And we sort of took a bottom-up approach here where we asked what kind of structural properties are important to support. So, is it sparse? Does there have a background value? Are the features actually like contiguous? Are the features repeated? Do you have like several contiguous homogeneous features? And then, of course, if there's only one feature in every row, then maybe we can avoid emitting a loop for that particular dimension. And so we sort of take the Cartesian product of all of these properties, and we come up with a wide variety of these one-dimensional formats. And then we can nest the one-dimensional formats to produce this parameterized language of different structures that we can express in Finch. I know that this is a very complicated diagram. I'll give you my favorite. I think if you nest an interval structure with an interval structure, you have a very cute little bounding box here. So this is a wide variety of features that we can represent. Now, the trick is combining control flow and data structures in the same program. So to do this, we introduce a notion of scopes. We have our declaration statements with this dot equals syntax, and we're going to restrict tensors to have only two modes, readable and writable. This allows us to construct the tensors efficiently. And then when we change between modes, between writable and readable, we have a few core interface functions that each of these structures needs to implement. So we'll call the freeze function here, and then if we transition from reading to writing, we'll call the thaw function. We restrict tensors to only change their modes in the defining scope. And this is what allows us to treat the tensors as constant when they're on the right-hand side and use this looplet concept to lower an individual loop. So this is a prior work that sort of represents a rewriting-based progressive lowering strategy to tackle the one-dimensional case. I'll give a little case study here. If we wanted to implement breadth-first search in Finch, we can talk about what kind of optimizations are required, and then how we would implement that. So the core idea of breadth-first search is that if we represent the frontier of nodes that we're currently visiting in a one-hot encoding, then we can say a vertex should be added to the next frontier if we haven't visited it yet, and one of its neighbors is in the current frontier. So that's what this equation is saying. Row major approach would be a really standard way to do this. You might represent this operation as a row major matrix vector multiply. But there's a few optimizations we can do. So if we iterate column major instead, then we can restrict our iteration to only visit nodes that are currently in the frontier. This is kind of a straightforward approach. But one thing you may notice is that if we're in the row major paradigm, then we can use the set of vertices we haven't visited yet as a filter instead. So you have a choice between these two different filters. Furthermore, if we're in this row major pole-based traversal, you can also use short circuiting, right? It doesn't matter how many neighbors are in the previous frontier that you're adjacent to. You just need one. So as soon as you find one, you can stop. Then there's a few structural optimizations you might do, which I don't have a very cute image for, but if the edges have weights, for example, you might represent a structure that only has the pattern of the matrix rather than the weights as well, and then you can simplify the code. You might also fuse the calculation of the parents together with the calculation of the next frontier, so that's another optimization you can do. And here it is in Finch, push and pull traversals for breadth-first search. There's a few features I'll point out here. We have our declaration of all of the structured inputs. We have two different loop orders. So the push traversal is the column major, and the pull traversal is the row major. We have conditional masks, which are masking off based on which vertices we've visited. And we have fused statements. So we can fuse the calculation of parents together with the calculation of the frontier. We represent short circuiting as a structural property. It's an odd choice, but this helps us integrate the effects of break with other structures in the program. So we chose to do this as a structural property of the input. And we see here the performance is competitive with the state of the art. So the red line is graph flaws. Both of them represent a speed up over Julia's default graph algorithm. Finally, I'll say Finch is an extensible system. This was accepted in the round 1 of OOPSLA', but we have several works that build on Finch using this kind of, using our control flow interface to precisely describe what kind of iteration and data flow is needed to do things efficiently. So one example here is we had a compiler called Systech, which generated symmetric optimized code for sparse inputs. So the way that this worked is that it used the control flow constructs of Finch to emit things like filters that only iterate over one triangle of the symmetric input. Another effort that we have going on is that we had a database query optimizer used to actually optimize high-level API calls down into Finch calls at the lower level. And so this was an instance where being very precise about the data flow and the control flow that you emit was really useful. And in the next talk, well, the next talk, you'll see my colleague Jayan describe a system that uses Finch to iterate over continuous values. So we kind of pun on what values an array can be indexed by to allow it to be indexed by real values. So with that, I will take any questions that you have, and we'll go on to the next speaker.
We have time for a very quick question.
We'll do the next speaker.
Yeah, so if you have any more questions, due to the sake of time, we have to stop now. But if you have any other questions, please talk to the speaker afterwards.
I'm here all week.